So our next topic is related to the adsorbed water and hydroxyl on the moon, and this is important for understanding the mobility of lunar water. And most of this short course has been discussion of the polar cold traps, and as you know, there's another potential sink or source for water at the lower latitudes. And so Jean-Philippe Combe, who is working with Tom McCord at the Keck Institute, is going to tell us about some results from M-cubed and models.
Thank you, Paul. Good afternoon, everyone. I'm going to take this opportunity to talk a bit more about near-infrared spectroscopy, because Tom and I have been part of the M-cubed team, and we are still working on the data. So this is the outline of my presentation, from the distribution of volatiles to the variations of the signal. And I'm going to make the distinctions between the variations of the signal and the interpretation of the mobility of volatiles. So prior to the observations, there have been models for the presence of volatiles at the surface of the moon as early as 1961 by Watson et al. And so I'm going to talk about, to present background information about elemental hydrogen, and then before coming to infrared spectroscopy and the distribution of OH and H2O, because I want to compare the two types of results. First, this is a background slide about neutron spectroscopy. So briefly, the elemental nuclei on lunar materials are excited by galactic cosmic rays that produce fast energy neutrons, and these neutrons lose their energy from collisions with other elements. And the range of energies we measure for the hydrogen is called epithermal neutrons. And the rate of energy loss of epithermal neutrons is sensitive to the abundance of hydrogen. And what is important to know in this kind of measurements is that neutrons flux integrates the sources within the 1 meter below the surface, which is very different from near-infrared spectroscopy. So this is a background slide about near-infrared spectroscopy. What we measure here is photons, and the photons from the sun that are reflected by the surface. And spectra represent the proportion of light, for example, this one, proportion of light reflected by the surface as a function of wavelength. And the unit is either reflectance or I over F, which is the reflectance factor here. The spectra, so these spectra have local minima, just as, for example, here, and this is called an absorption band, and it is sensitive to the molecular composition, the molecular bonds, actually. OH and H2O have an absorption band, very broad and asymmetric at 3 micrometers, actually between 2.7 and 3.5 micrometers. And I'm going to talk more about this absorption band. Depending on the vibration mode of the molecular bond and the type of constituent, for example, between H2O ice and adsorb H2O, the shape of the bond vary. The spectra on the left are laboratory spectra. On the right, all these spectra are lunar spectra taken from orbit and from 3 different instruments. The first one is a M-cubed dataset so the moon mineralogy mapper, which stops at 3 micrometers, so right inside the band of OH and H2O. So that makes the analysis a bit challenging. But we do observe the first part of the absorption band. Other instruments, such as spectrometer on the Deep Impact mission and VIMS on Cassini, have also observed this absorption band. And we have here the entire range of wavelengths. I would like to mention there is also an absorption band here that is due to pyroxene. It's a component of basalt, and I'm going to talk a little bit more about this later. So that was the first detection of OH or H2O at the surface of the moon from near-infrared spectroscopy. After this first detection, there have been investigation of the character of the variations of this absorption band in M-cube data. And as you can see, sometimes we have a narrow band here, and sometimes it's much broader. So that could be the possibility of making the distinction between OH and adsorbed H2O. So we have made this analysis where, well, for example, here on the lower left, we have a 2D scatter plot of the 3 micron band as a function of the 2.8 micron band, just to measure the shape of this band. And, well, there is a diffuse correlation with different regimes of positive correlation, for example, this one here, this one here, this one here. These plots are function of latitude, and in both cases, 2.8 micron, 3 micron, we have variations as a function of latitude, a minimum of the absorption at the equator and maximum near the poles. So this is consistent with higher abundance of volatiles near the poles. But this is not a formal, this is not a real demonstration that we can make the distinction between H2O and OH. So we have to be aware of this. There is a complex variability in this region, but that may not be due to the different types of constituents. In the ultraviolet, there have been also detection of H2O. So this is the same principle than in the near-infrared. It's also reflectance, but the absorption band in this case is here at 165, 175 nanometers. And this is models of mixed spectra with the content of H2O. And the spectra on the left are actual spectra from the moon that show also this absorption band. And the absorption band is deeper on lunar highlands than on mare basalts. So this is consistent with the observations on the near-infrared. Now I would like to make a comparison between the observations from neutron spectroscopy and from the near-infrared. So these are two global maps, hydrogen map and the OH, H2O from the near-infrared on the right. There are similarities, for example, the enhancement of volatiles at poles. This is similar in both maps. Also, the variation as a function of latitude. This lower left graph is a neutron count as a function of latitude, which is the opposite as the hydrogen content. And this is similar to the depth of the OH band at 3 micrometers. However, there are significant differences, such as, well, in the near-infrared, there is a strong dichotomy between highlands that are all blue here and mare basalt that are darker region and that are well, do not have an absorption band in this case. This dichotomy is also illustrated by this 2D scatter plot here. This is the absorption band at 3 micrometers as a function of the pyroxene absorption band. And there is this anti-correlation that is consistent with the dichotomy on the map. This is very different from the elemental composition, especially in the Mare basalt. There is a very complex distribution in the hydrogen content here. So, well, we have talked a lot about polar regions already. This is just an illustration of the maps of elemental hydrogen from 2 different spacecraft at almost 2 decades apart, and the highest content of hydrogen is observed in permanently shadowed regions. There have been, well, investigations of these polar regions in the near-infrared also, but only from L-cross. And it's not an observation of the surface, it's observation of the plume following the impact. So it's a little bit different from what has been mapped in the near-infrared and from other regions. However, there is, well, these spectra taken at different times after the impact have been interpreted in terms of presence of H2O, especially because of absorption bands at 1.4 micrometers and 1.9 micrometers. All right. In the near-infrared, we have some significant limitations for mapping volatiles because we use the solar illumination reflected by the surface. Well, at the poles and especially in permanently shadowed regions, by definition, we don't have a direct solar illumination. So we don't have, the signal is not good enough for interpretation of the spectra. And it's different from images of high resolution cameras we have seen earlier, where we can see some details of the topography in deep shadowed regions. But we don't have similar data sets in near-infrared spectroscopy. So now I'm going to talk about variations of the signal and further limitations in the interpretation of the data. The first investigation has been made from data acquired by the Deep Impact mission. We have seen this morning spectra acquired at noon and the evening of the 3 micron band absorption band. The graph on the right shows the depth of the band as a function of lunar local time of day, and we see the variation. The band is the most shallow at noon lunar local time. So this is a suggestion of temporal variations of the band and therefore of the content of H2O and OH. Well, in the near-infrared, we have to be careful about such variations. And I'm going to first focus on the spectra on the right here. This is M-cube spectra. So the actual M-cube spectrum is a white one here that shows the absorption band at 3 micrometers. When the surface is illuminated, it becomes very hot, and therefore thermal emission starts to contribute significantly to the signal. And this is a model simulation of thermal emission contribution. So you see it becomes significant at 3 micrometers. And it's additive to the reflectance. So when the thermal contribution is added to the M-cube spectrum, it becomes the spectrum in cyan here. And it almost fills completely the absorption band of at 3 micrometers. Therefore, when the surface is rich in volatiles, there is an underestimate of the thermal contribution, and therefore there is an underestimate of the absorption band at 3 micrometers. So we underestimate the content of volatiles. And it's very challenging to make an accurate correction in this range of wavelengths because the instrument stops at 3 micrometers. We don't have the other part of the absorption band. So we need independent modeling of the thermal contribution, and this is a topic I'm working at the moment, but I'm not completely done yet. On the left, I'm trying to illustrate the consequences of this thermal contribution. So this first set of spectra are 2 spectra of the same region acquired in the morning and in the afternoon. So you see variations in the character of this 3 micron band. And the cyan spectrum here is a ratio of those 2 spectra. And you see the shape of the ratio is very similar to the shape of a thermal emission. So the previous attempt we made on characterizing the diversity of the shape in this range of wavelengths might be simply due to thermal emission contribution. Fortunately, we have counterexamples of this. This is a similar type of ratio, morning and afternoon spectra, and ratio of the 2. Well, we see also this upward spectrum here that looks like a thermal emission contribution. However, we have also this kink here. We have a kind of a breaking point here that might be due to that might not be due to thermal emission, and therefore it could be due to variations in the contents of H2O. So we have a few examples like this where, well, with MQ we can detect variations that might be consistent with observations by the epoxy mission. All right. There have been similar investigation of temporal variations in the ultraviolet as well, with a lamp instrument. So again, this is the absorption band of H2O, and the slope between 165 and 175 nanometers is very sensitive to the absorption band of H2O. And this is a slope, and this is a slope here. And so this one is for variations as a function of latitude, and we see the slope becomes more positive as latitude increases. So this is consistent with the results from the near infrared. The spectra in the middle are for diurnal variations. So these are 4 spectra acquired at 4 different beta angles. The beta angle is sensitive to, well, is a function of the lunar local time of day. So 0 beta angle is for noon lunar local time. And at noon, the slope is the most negative, so it's when the band is weakest. And for the largest beta angles, the slope is the most positive. So this is consistent with diurnal variations of the H2O content. However, I'm going to present another effect that may limit the interpretation of this of these variations. I'm going to talk about photometric effects. The photometry is due to variations of the geometry of illumination and observation. So this is an illustration with M-cube data again, but this works similarly in the ultraviolet. So the first row is data from acquired in the morning, and the second row is the same region. You can recognize the crater here with illumination, well, in the afternoon. So the sun illuminates from the left in the afternoon and from the right in the morning. So this is just reflectance. The first column is reflectance. The second column is absorption band depth at 3 micrometers, and it shows very strong variations. And as a test, I mapped the absorption band depth of pyroxene. So we don't expect the content of basalt to vary as a function of illumination. And we do see in the absorption band depths, we do see strong variations. And these variations are very similar to what we observed at 3 micrometers. So this illustrates a strong photometric effect that we have to correct in order to interpret variations as a function of time of day. Well, at 3 micrometers, this is very challenging to do because we have to remember that the thermal contribution is very significant also. And in order to develop photometric correction, we need thermal correction. And for the thermal correction, we also need a photometric correction. So the two types of corrections depend from each other. And there have been several groups of researchers that have worked on this topic, and in order to develop independent models for corrections. But all these models still have serious issues, and I'm working on this topic at the moment. Well, I talked a lot about limitations in the near-infrared. Well, there are also positive aspects, but limitations also exist with other measurements, such as the elemental hydrogen. For example, we cannot, well, I'm not aware of any investigations from temporal variations of elemental hydrogen, and it's maybe simply because it's not possible. The neutron flux is so low that we have to integrate over a very long period of time in order to acquire some enough signal. And furthermore, neutron flux is integrated over 1 meter below the surface, and this large distance may be enough to smooth out any variations, diurnal variations. Now I'm going to talk about models for the origins and delivery of volatiles at the surface. I'm going to make the distinction between models of delivery of volatiles and models of distribution at the surface. There are 3 main models to explain the presence of water and OH at the surface of the moon. One is implantation of protons from the solar wind. The second is infall of meteorites and comets that are rich in volatiles. And the third one is endogenic volatiles. None of these models explain the distribution of volatiles that we observe. And for example, this map here is an illustration of the flux of solar wind particles that reach the surface of the moon at a given time. And the flux is the highest at the equator, and in this case, well, for the sun-facing area. And this is different from the distribution of volatiles that we observe at the surface, where we have enhanced hydrogen at the poles. So that illustrates that the models to explain the origin of volatiles, the presence of volatiles at the surface of the moon, have to be distinguished from the models that explain the distribution of volatiles at the surface of the moon. That's why I'm going to talk briefly about the origins of volatiles, and then at the end of the presentation about the mobility of the volatiles. All right, the first model is about the implantations of protons from the solar wind. The lunar material at the surface undergoes constant micrometeorite bombardments that damage the molecular bonds, and therefore minerals may have dangling O- bonds that may accept any positively charged particles from the solar wind, and especially protons, to form OH. And the cartoon at the right here, lower right, illustrates the oxygen with arms wide open that may accept an incoming proton to form OH. Furthermore, well, okay. So this idea has been thought very early, already in the 1960s, and it has been at the time simulated in the laboratory by bombarding a surface of silicate by protons. And this is absorption band of at 3 micrometers, and the absorption band increases as a function of the flux of proton. And this graph illustrates the increase of the absorption band as a function of flux. The solar wind particles and the micrometeorite bombardment may vaporize some elements and some groups of molecules, such as native iron and SiO2. And when these constituents vaporize, then they may form deposits, very dark deposits, at the surface of the moon, and that is part of what we call space weathering and maturation of the surface. And this illustrates possibly the importance of the solar wind to explain the presence of OH. There are areas on the moon that have strong magnetic anomalies that are on the map here. And some of these magnetic anomalies are associated to areas called swirls that appear very contrasted, bright and dark. And the bright areas have will appear depleted in OH, as seen on the bottom here. And they also appear optically immature. So that is consistent with, that supports fully the model of the role of the solar wind in the formation of OH. The second model is, I'm going to be brief here, is about infalling comets and meteorites. Again, the swirls have been chosen to illustrate the role of comets, to explain the strange shape of the lunar swirls. That may not be that may be a little bit outdated today. However, there are still investigations about the flux of incoming comets and meteorites in order to explain the amount of volatiles that are observed today at the surface of the moon. And this has to be also compared with VESTA, where the maps of volatiles are more consistent with infalling comets and carbonaceous chondrite meteorites. So this mode of delivery may also exist at the surface of the moon. Well, finally, this is about endogenic water observed from the analysis of minerals, and higher contents of H2O at the core of grains of minerals than at the rim. That may suggest outgassing of H2O. So there are three main mechanisms that have been that we have thought about. All right. All these mechanisms may exist, and they may we may need all of them to explain the presence of volatiles at the surface of the moon. Now I'm going to finish my talk with the mobility of water at the surface of the moon. We know there is water, or OH, at the surface of the moon, but none of the models that I just talked about explain the distribution. They just explain the presence of water. And we have to consider that water, or OH, is transported from the point where they are delivered at the surface to the regions they are observed at the moment. And this illustration by Krider and Vondrak illustrate different processes that the molecules OH and H2O molecules may undergo from the delivery. The H2O may be dissolved due to variations of temperature, and when H2O is released, it's exposed to the space environment. It may be dissociated and subsequently lost. And some of these molecules may reach the surface again through ballistic trajectories, and subsequently they may become stable at the surface by condensation on cold traps. So that's one model of lateral transport. And there have been also modeling of vertical transport to explain the survival of molecules at the surface or at the subsurface of the moon. So I think I'm going to finish my talk soon here. The slide I had were just to illustrate in more detail what I just explained about the stability of H2O, the way it is absorbed and the way it can be released in order to explain the transport of the molecules from the equator to the poles. And so we have seen this plot already this morning. This is the contribution of molecules from low latitude that contribute to the volatile content at higher latitude. And this is another model, but this is different. This is for the vertical migration of H2O. So that explains how molecules may survive at the surface of the moon, or maybe subsequently buried beneath the surface, and therefore be present for long times. So this is a summary of what I just explained. So I'm going to leave this slide if you have questions. Thank you for your attention.